Welcome to Miss Math Tutorials. I'm Miss Smith. In this video, we're going to be talking about points of concurrency, and we're also within that, as we go through the points of concurrency, it's important to talk about the segments that create the points of concurrency. So we're going to kind of tackle both at the same time. Always on the top are going to be the segments that create the points of concurrency, and on the bottom, underlined, is going to be the actual points of concurrency. So the first segment that we're going to talk about is going to be medians. So a median is a segment that starts at the vertex. So when it says vertex, that just means it starts at an angle of a triangle. Okay, so notice in this triangle, it starts up here at the angle. Okay, so this segment starts at the angle vertex and cuts the opposite side of the triangle in half. And we can tell that it cuts it perfectly in half because of these tick marks right here and right here. What that tells me is that from here to here is the same distance as from here to here. So this right here is the median. So a centroid is a point where three medians meet. So the centroid is going to be the actual point of concurrency that's formed by three medians. What's important to understand about centroids is that they are always going to be on the inside of a triangle. I've shown three different pictures here of an acute triangle, an obtuse triangle, and a right triangle. Just some examples to show you that the centroid, which is, you see it, it's a point, and I've tried to really highlight that here, that is a point in the center, in this case on the inside of each triangle. Notice I have a median from this vertex cutting that side in half, a median from this vertex cutting that side in half, and a median from this top cutting the bottom side in half. Where those three medians intersect, right there, is called a centroid. And the segments that it creates, meaning like from here and here, these two segments are split in a 2-to-1 ratio. So what that means, and I'll just use this segment right here, for example, this median right here. So from here, split in the middle right there. So if I were to split that segment here and here, then this segment, and this segment are all the same equal distance. This one was 2, then this one is also 2, and then that would make this one 2. So that's a 2-to-1 ratio. The next segment that we're going to talk about is a perpendicular bisector. What does perpendicular mean? Let's remember that creates this like T shape right here. And if it's perpendicular, that means it hits at a 90-degree angle. It is perpendicular to this side at its midpoint. Notice what's happening. It's this line coming straight down, creates a 90-degree angle, and it creates two equal parts on either side of it. Cuts this side right at the midpoint. So this is the same distance as this. It does not have to start at the vertex. So notice this perpendicular bisector, I've purposely shown it coming down. Now, could it start at the vertex? It's possible in a different triangle, maybe that it could, but in a lot of triangles, you'll see the perpendicular bisector does not start at the vertex. A lot of times it'll start kind of like in the side because it's starting at the midpoint and then it's just going straight up. And the key word really is in the name itself. So it's perpendicular, it creates a 90-degree angle, and a bisector means it's cutting something in two. In this case, it is the side that it's cutting into equal parts. So the clues really are in the name with that one. Now we're ready to talk about the actual point of concurrency. So a circumcenter is going to be the point where three perpendicular bisectors meet. If I had three of these, they would all intersect at a point that we would call the circumcenter. What's important to understand about a circumcenter is it is not always going to be on the inside of the triangle. To show you that it's not always on the inside of the triangle, if we had an acute triangle with 3 perpendicular bisectors all intersecting at this one point called the circumcenter, notice it's on the inside of the triangle. But if we had an obtuse triangle, notice I've got a perpendicular bisector here, here, and here. We would actually have to extend those bisectors. Notice I've done that with these dashed lines. We would have to extend them beyond the triangle to see where they intersect. And in this case, it occurs outside of the triangle. And if we had a right triangle, a circumcenter would actually, once I draw these perpendicular bisectors, if I drew them perfectly, the circumcenter would fall actually on the triangle. A circumcenter is equidistant from the angles. If I were to measure the different distance from this angle to the circumcenter and from this angle to the circumcenter and from this angle to the circumcenter, it would be equal distance. They would all be the same distance. Okay, let's look at our final 2. We have an altitude. Now, an altitude can look really different when we have an acute, obtuse, and right triangle. So I've drawn each of those so we can kind of see. But an altitude is essentially the height of the triangle. Always starts at a vertex, and it forms a right angle. Again, it looks really different. So an acute triangle, notice it starts at the vertex, it comes straight down, and it's literally like, how tall is this triangle from one vertex to the other side? It does create that perfect 90-degree angle. So a lot of students tend to get altitudes and perpendicular bisectors confused. And I see that that could be easy to do, particularly if it's an acute triangle, and they see that 90 degree and they want to call it, oh, it's a perpendicular bisector. But we have to keep in mind, a perpendicular bisector creates 2 equal sides. And if these were equal, they would have tick marks. And in this case, they don't, so that means we cannot assume that they're equal, so that would make this an altitude. So just kind of keep that in mind. And then for the obtuse triangle, notice this altitude is actually outside of the triangle. And if we have a right triangle, the altitude will be actually on the triangle. Now, let's get to the actual point of concurrency, which would be our orthocenter. Our orthocenter is a point where 3 altitudes meet. Notice if I had a height, an altitude here, an altitude from that angle, and an altitude from that angle, where they all intersect is called the orthocenter. And an orthocenter is not always going to be on the inside of a triangle. So again, if we had an acute triangle, our orthocenter would be on the inside. If we had an obtuse triangle, and this can be kind of hard to see, and it was definitely hard to sketch, but if we were to take the height from this vertex and the height from that vertex, now I know that feels weird. You're like, how is that the height? You would have to actually flip this picture around so that this is now the base, that's on the bottom, and then you could see that this is the height. I'm not going to do it because it's going to kind of mess up my setup here, but this would be our extending height for that vertex. And then this would be the height for that vertex. But if we were to extend each of these beyond that point, eventually we would find the orthocenter, and it would be located outside of the triangle. That is a tricky one. And then if we had a right triangle, the orthocenter, so if we were to measure the height of each of these, would actually be on the triangle. Our last section that we're going to talk about, first we're going to talk about the angle bisector. The angle bisector is pretty easy to identify because notice it's a segment that cuts a vertex angle in half. In this case, this right here would be our angle bisector. So this would be the angle bisector, but notice what it's doing. It's taking this angle and it's cutting it perfectly down the center so we end up with an equal part here, and here. Okay, and we see that with the little angle with the tick mark. What it's saying is that that angle degree is going to be the same value as that angle degree. So these, again, pretty easy to identify. Now, let's talk about the point of concurrency. So an in-center is going to be the point where three angle bisectors meet. So if we had an angle bisector for this vertex, and for this vertex, and for this vertex, they would all intersect at a point called the in-center. So an in-center is always going to be on the inside of a triangle. So another good note is that the in-center is equidistant from the sides. If we were to measure this distance, and this distance, they would all be equal to each other. I noticed that this does not form a right angle. And a lot of people want to just add a box there. We can't do that. Even if it looks like a right angle, we cannot add that. They didn't tell us that, so we can't just magically add one, okay? So there's no right angle, which means immediately I know this is not an altitude, and I know it's not a perpendicular bisector, because both of those would have to have a right angle there. And other observations I noticed, look at what happens. It creates an equal part here and here. It cuts this in two. You may need to look back, especially if this is, new for you. Remember that a median is the segment that will cut a side in half, yet it does not create any kind of 90-degree angle. Okay, that's called a median. So we got to think, okay, they don't want to know the segments that are going on. They want to know the point of concurrency. So when I have three medians intersecting in one point, what is that point? And that is called you may need to look back, but that's called a centroid. Okay, so our point of concurrency is a centroid in this case. And if you want to note off to the side, three medians, that could be helpful as well. So now we need to solve for any unknown variables. The first thing I notice is that we have this tick mark labeled, or that side I should say, labeled 5x minus 3, and then this side labeled 3x plus 1. And those tick marks tell me that these two sides are equal. Let's go ahead and set them equal, because if I set them equal, I can solve them for x. So let's say 5x minus 3 equals 3x plus 1. So when I subtract 3x, we just use our basic solving skills here. 5x minus 3x is 2x. And then I still got my minus 3 equals a positive 1. Now I want to get my x alone, so I need to add 3 to both sides. And I get 2x equals 1 plus 3 is 4. My final step to get x alone is to divide both sides by 2, and I get x equals 2. Okay, so there's one of my variables, right? X equals 2. And then there's also a y, though. They're wanting to know if this segment from here to here is 10, what is the distance from here to here? So if you review back where we talked about centroids, we said that they're split in a 2-to-1 ratio. And so I like to visually think of that like this is 2 parts and this is 1 part. Okay, so if I were to split this part, just visually split it in 2, right? If I know the whole thing is 10, then what is this and what is this? So we got to think, okay, well, what's half of 10? 10 divided by 2 is 5, right? So from here to here is 5, and from here to here is 5, then from here to here is 5. Okay, they are split in a, so we could say y equals 5. They are split in a 2-part to 1-part ratio. All right, let's look at this next example. So immediate observations, and hopefully you're seeing the same thing, is that I've got angles marked. Okay, remember, angles being marked, that is a very big red flag that we are talking about angle bisectors. Notice I don't have any tick marks on sides. This is probably an angle bisector, and when you look at it, you can tell it is, because when I look, each segment is splitting an angle in two equal parts, right? Here and here, here and here. So if my segments are angle bisectors, remember they want to know the point of concurrency. What is that point called if we've got all angle bisectors? And you may need to review, but three angle bisectors form an incenter. Okay, so our point of concurrency is an incenter. Now, as far as solving for, in this case, we've got an x and a y we need to find. If this angle, it's telling me, this little arrow is telling me that from here to here, just that little bit of angle is 22 degrees. And then they're saying, so what's this little bit of angle, right? Well, remember, an angle bisector cuts an angle perfectly in two. So if that side's 22 degrees, then this side, x, is also 22 degrees. And now to figure out y, you may be thinking, okay, well, I don't know that side. I don't know the total there. We've got to use a little bit more of our background knowledge to figure out y. So let's think, if this was 22 and this is 22, then the whole thing, this whole side, is 44 degrees. So let's think, if this angle is 44, notice what this angle has. It's got that little box there. And notice I do have this angle marked, but even inside of that, I've got that box. And remember, that little box means 90 degrees. So this is just telling me it's a right triangle. Okay, so if this angle is 44 degrees, right? And this angle is 90 degrees. How could I figure out what that total angle is? Well, what do all triangles, what do their angles add up to? And hopefully you're thinking 180 degrees. Let's think. I've got 44 and 90. So let's add those together. What is 90 plus 44, right? And that ends up being 134 degrees, right? And then we know the total is 180. So let's subtract the ones we know, the total of 134. So 180 minus 134 is 46 degrees. So, okay, I know this whole total angle is 46 degrees. But they don't want to know the whole total. From that arrow, they're telling me they just want to know one part of it, just half of it. So I would say, okay, well, what's half of 46? And we get 23 degrees. So in this case, x's are 22 and y is 23 degrees. Okay, in this example, let's make some observations. So again, if you try to look at all the segments at once, it's overwhelming. So just focus on one. Just focus on this one in the center. So I know it's coming down from the vertex and it's forming a right angle. Okay, now is it cutting this into perfect equal distances? No. If it did, I'd have a tick mark there and there telling me. So the fact that it forms a 90-degree angle means it's got to be either an altitude or a perpendicular bisector. And when I look at this, and I can tell that it's not cutting this side in half, which means it could not be a perpendicular bisector. So this has to be an altitude. But remember, they didn't ask me about just one of the segments. They want to know the actual point of concurrency. So what do three altitudes intersecting form? It is called an orthocenter. To solve for my unknown variable here, notice it's pointing to this little boxed angle, and it's saying that angle is 2x plus 7. So we know anytime we have a little box in our angle, that means that angle is actually 90 degrees. I can take 2x plus 7 and set it equal to 90 degrees. And then from here I can solve for x. So I would want to subtract 7 from both sides. And I get 2x equals 90 minus 7 is 83. And then when we divide by 2, definitely going to get a decimal here. You could say it's 83 over 2 or 41.5. All right, let's look at our final example. So we start from the vertex and then it comes down and it forms a right angle. Immediately I'm thinking, all right, altitude or perpendicular bisector. Let's see which one it is. Does it cut into 2 equal parts? Yes, it does. Okay, I see that because it tick there, tick there. So that means this is not an altitude, it is a perpendicular bisector. But let's think, they didn't want to know what the segment was. They're asking what the point of concurrency is, what that point in the center is. So what happens when I have 3 perpendicular bisectors? They intersect and form a circumcenter. And then to figure out our x for this one, we know these two sides are equal to each other, but I don't know what that side is, so that doesn't really help. What I see is that this is 2 from here to here, and that from here to here is 8. Looking at that, and I'm hoping maybe some of you are looking at that and you're thinking of what I need to do, but if you're not, maybe I'll draw this and it'll help. Okay, if I've got, look at the shape that forms right here. Look at that highlighted area, and hopefully you're recognizing that that is a right triangle. In a right triangle, if we have 2 sides and we're missing a third side, we can use something called, maybe you're thinking of it, I hope so, Pythagorean Theorem. So remember, Pythagorean Theorem is a squared plus b squared equals c squared. Basically, we can use Pythagorean Theorem in a right triangle if we know 2 sides and are missing a third side. We've got to remember that A and B are interchangeable, meaning they're my 2 shorter sides, and it doesn't matter which one I make A and which one I make B. It makes no difference, right? But the C has to be the hypotenuse. It has to be the longest side. It's called the hypotenuse. In this case, I'll just make 2 my A. B, I'm going to call my X, since that's what they're calling it. And C is my hypotenuse, so that's that 8 squared. Now to solve this from here, I would actually want to say, okay, what is 2 squared? Well, that's 4. And what is 8 squared? Well, that's 64. And then I do want to try to get my x alone, so let's subtract 4 from each side. 64 minus 4 is 60. And then remember, they don't want to know x squared, they want to know x. So I've got to get rid of that little square. And hopefully you're thinking, well, how do I get rid of that little square? I take the square root. And when I do that, the square root and the little 2 cancel each other out. So all you have left is x. But if we do that to one side, you have to take the square root of the other side too. So square root of 60. Personally, anytime we're dealing with a measurement or a side, I like to just have a decimal answer. But you may be in a situation where your teacher or a particular test is asking you for a simplified radical. So I'm going to give both answers. And so we could just bring out our calculator and type in square root of 60. We're going to get a decimal because 60 is not a perfect square. Your answer, if your teacher is okay with it, or your test, whatever, if they're okay with it, then your answer would be 7 point, and we'll just say to the 10th place, 7.7. And that's a rounded answer, and if that's good enough, then great. If they ask for an exact answer or for a simplified radical, then we're going to have to simplify this radical. Now, we would ask ourselves, okay, what goes into 60? Immediately, I think of 6 and 10. And can I break 6 down any further? Yes, to 3 and 2. Can I break 10 down any further? Yes, to 2 and 5. Remember, it takes a pair to bring out 1 in the radical. So I've got a pair of 2's, and 3 and 5 do not have a pair. They don't have a buddy, so they're stuck in the radical tied through multiplication. So that is 1, 2 that gets to come out. I'm going to put a little or because our answer could be 7.7, or the 2 that gets to come out, and then underneath the square root would be 3 times 5, which is 15. Couple just quick notes I want to make about this. This is, again, a rounded answer. This is an exact answer. I know I have really tried to push in my videos that anytime we take the square root of a number, we have both the negative and the positive version. So typically you would see a little plus and minus out front here and a little plus or minus out front there. I'm not doing that here intentionally because this is a measurement of an actual object. Could I really have positive 7.7 and negative 0.77? Well, could we have a negative 7.7 measurement? No. Not in a real life situation like this where we're creating measurements. In this case, I'm purposely not showing the negatives as part of the answer because they wouldn't make sense. Okay, so here's 2 for you guys to try on your own. I will post the answer in the video description below. This has been Miss Math Tutorials.